So this is a very simple, easy little application. So I hope everyone will at least understand what we did, if not necessarily think that it was a good idea. Um, so the focus here is on astronomical images. And these might be quite different in property than maybe a lot of images that other people process, where, in fact, noise is really the limiting factor. So we actually believe that, at least for high-quality scientific CCD kind of images, we actually have IID Gaussian noise as like the dominant thing contributing to each pixel. So to give you kind of an illustration of this, on the bottom I've got a series of a bunch of real data from the Sloan Digital Sky Survey. And you can see that basically if you have a single exposure, if you kind of squint, you might be able to believe that there are two bright objects in that image. And if you start adding together multiple exposures, so doubling the exposure time, quadrupling the exposure time, the signal is adding up and the noise is being averaged down as square root. And as you add sort of more and more exposures, you actually start to see these things very clearly. And in fact, a third object kind of pops out just above the kind of orange one there. If you're not an astronomer, you might be squinting saying, really, really? But if there were astronomers in the crowd, they'd say, oh yeah, of course. That's clear. OK, so if we had these beautiful, well-calibrated linear images, we could reduce the noise by averaging together multiple images. And that would expose more objects. That would give us more reach in our science. But that really only works if they're calibrated in the sense that they're measuring the same thing, or they're scaled in the same units. And we're going to look at a case where, or a situation where that's not the case here. And I'll say just as an aside that people always ask about how do you get your images aligned? How do you get them registered to each other? That's a solved problem. I'll mention it very briefly, but we're going to just assume that as a given. So if you do other kinds of computer vision, we're just assuming that the hardest part of the problem is already solved. So I apologize for that part. You won't learn anything about in this talk if you deal with images from the 3D world, probably. OK, so what we're looking at here is, given that if we could combine many images, we'd get more sensitivity, and then we'd discover more things. So of course, we'd like to make use of all of the images on the web, or try to recruit people to contribute lots of images, to go out into their backyards or use their observatories and telescopes and cameras to collect images for us. But of course, the problem here is that, and the problem we're tackling in this work is that these images are always going to have nonlinear stretches, or nonlinear mappings applied to the pixels. And this is particularly the case for astronomical images, because the dynamic range is huge. So just along the bottom, I have a couple of nonlinear mappings we might encounter. And you can sort of see the problem. If you just plot, make it so that the darkest pixel is black and the brightest pixel is white, you get nothing. You can sort of see that there's one pixel on if you look at my screen. But this is the typical problem of giving talks about astronomical images. You can't really see anything. It looks like a big black nothing. Whereas, if you stretch it so that from the first percentile to the 99th percentile, you kind of see that there's stuff there. But then to really pull out some of the details, people do kind of complicated, strange, nonlinear mappings. OK, so you might say, all right, so you're going to try to learn those nonlinear mappings. Nope. Instead, in this work at least, we punted and we said, let's just not try to learn and back out those nonlinear mappings, but instead just assume they're monotonic and then work purely with ranks. So um, treat an image rather than a series of measurements that have gone through some nonlinear mapping. Instead, just think of them as a ranking of the brightnesses of pixels or brightnesses of different parts of the sky. And so then now, instead of averaging together images, we want to build some sort of consensus ranking of where the darkest and brightest parts of the sky are. Okay, so that's basically the setting that we're trying to work in here. All right, so here's the dead easy algorithm in kind of English pseudocode. So as I said, we're going to assume we're given pixel-aligned input images. We'll initialize a consensus image and a vote count. When I gave this talk to astronomers, the main complaint was about calling it a consensus image because it's really a voting sort of thing, so it's not at all really a consensus. It's kind of a winner takes all. So anyway, we initialize the consensus image. It can really be initialized with basically anything. But you could think of it, it might be easiest to think of it as simply integers from 1 to the number of pixels, from like 1 to 10 megapixels or whatever. And the vote count to just like some small number. And then basically for each image, we're going to have not only the image, but also a mask that says which part of the area of interest it covers. So not all of the images cover the area entirely. And then essentially, for each of those, we'll compute the rank in the new image and that masked area in the consensus, and combine those two rankings in some way. And here we did a dead easy weighted average rank. So if 4 images have seen a pixel so far, and they've ranked it at 20th percentile, and the new image ranks it at 25th percentile, it bumps up to 21st percentile. Did I get that right? Approximately. And then once we've done that, we'll then permute the pixels within the consensus image in the masked region so that they're again sorted. And then just increment the vote count within that area. So it's really, really dead easy. All right, so I'll tell you about a couple of the experiments we did here. And for time, halfway, perfect. All right, so we started with doing web image search for this particular galaxy, NGC 5907, using Bing, Google, and Flickr. We run astrometry.net on each. That's the thing that does the registration for us. So this both identifies images of the night sky and registers them. And then we'll run this dead easy algorithm on those results. So here I'm showing a few of the results from the web image search. The ones marked with green stars were actually recognized as images of the night sky and localized. So you can see that there's it's cute, there's a book cover. This one's not as good as some of the results. So even for this fairly unique search phrase, NGC 5907, you get a lot of astronomical themed images, but actually very few of that particular object. So it's, we found this returned something like 1,000 search results, or maybe 2,000, and 2 pictures of cats, confirming our previous finding that 0.1% of images on the internet are cats. So anyway, after running astrometry.net, we can identify images that overlap the area of interest. And then, so you can see they're all kind of pictures of this. This is an edge-on spiral galaxy, so we're kind of looking at a flat spiral galaxy from the side. And then after pixel registering them, they're sort of all in the same orientation. Okay, and then, so I'll take an aside for one slide and tell you about this astrometry.net system. This is often like what people are actually interested in when they see the poster. So you can think of this as the problem of we give you an image and you give us an image and we tell you where it is on the sky. So the steps are basically that of detecting stars in the image. And then it looks at a subset of 4 stars and computes a geometric hash of that, of the local arrangement of those 4 stars. And that gives you a 4-dimensional code that is scale, rotation, and translation invariant. So we then look up that hash code in a large index that we've previously built. And that produces a bunch of matches that says those 4 stars could be these 4 on the sky, or these 4 in the sky, and so on. And for each of those matches, we then have to ask, all right, that's a prediction that if this image in fact belongs on that part of the sky, then we should see other stars at a bunch of particular locations. And we can assess how good that prediction is. I don't know if how well you can see, but here you can kind of see that there are you can count maybe 10 places where a star in the image basically lines up perfectly with one that was expected from previous measurements. So, we evaluate that with a Bayesian decision theory framework and accept one if it has basically overwhelming evidence. So that is just kind of a brief look at that system. So now back to looking at some of the results from this NGC 5907 data set. I'll show you it iterating through a few images. So basically, the new image is in the top left here. It's rank ordered image, or like histogram equalized image, is in the bottom left there. So the darkest pixel is pure black, and the brightest pixel is pure white, and the median pixel should be middle gray. In the top right is the consensus image after this one has been incorporated. And the bottom right is just the consensus image with a nonlinear mapping to make it look nice. So you can see that the consensus image started out basically as pure noise, and then where the new image came in, it's basically dominating. All right, so next we get, say, a small image that covers just the middle part. And I'll flip back and forth for a second. You can see that it only changes the consensus image within its footprint. And this one happens to just kind of tidy up the middle of the galaxy a little bit. Okay, so just adding in a few more, you get this one's actually a nasty one that I think that exposes a problem we want to fix. Here you can see that this kind of ripply rainbow pattern in the rank-ordered image. And that's, even though you can't really, even if you look at it on a computer screen, you can't see anything in the background, in the real image. It's basically just, very small variations in the background level, or like different shades of black in the background. But since those actually correspond to fairly large differences in rank, it kind of makes a mess of the consensus image at this point. Although still, when you look at it in the mapping the consensus image back through nonlinear mapping, it still kind of looks okay, but it's done some damage. Still, averaging down, that should kind of go away, one hopes. And then, so here it is after 6, and then I'll flip straight to 298, the total number we found for this galaxy. And you can see that it looks fairly reasonable, but it still has some of these kind of rainbow gradients. So I think this is kind of the big, easy thing to fix. Should have fixed it yesterday, but And since who doesn't love watching algorithms work, I'll just play the movie of it sort of building up. And then probably have to, yeah. Okay, so here's again just a plot of the results. And now on the left are our results, and the right are kind of what you can think of as ground truth, a very deep image from the world's expert in in taking these very long exposures. And a really notable thing in this galaxy is that big loop, that big arcing stream around the galaxy, right? Like especially in the bottom. That was actually the kind of feature that we were going after in the first place when we started out this work. This happens in general when two galaxies interact. So what's happened here is there's this big spiral galaxy, and a little galaxy has come along, come near it, and been torn apart by the big galaxy's gravity. So all that's left of this little galaxy is this stream of stars. And that would be hundreds of millions of stars. You can't see them individually. You just see this basically faint haze. And in short exposures, it's totally dominated by just noise from mostly from the Earth's atmosphere. Whereas if you can start to add up in a lot of exposures, these faint features start to pop out. And if you squint and you're generous, you can say, well, you can actually start to see it in our image here with just 300 exposures. So whereas this is a months-long effort, we started to get toward finding something like that with a web search. So that seems like at least a promising start, even though it still looks a little bit ugly. All right, so we thought that was only with 300. What if we had more images? So we did another test with this galaxy M51 that's, again, a pair of galaxies. So there's the big spiral in the bottom and another nearby galaxy in the top. They've basically just had their first pass by, so the little one hasn't been torn apart yet. It probably will be. And this is a really popular target, so we thought there's going to be tons of images of this. We got something like 2,000, so you really start to get a bit of a sense of how it's going to perform as we start throwing in more images. And the result kind of looks much more clean than in the previous example. So partly, this is big numbers will save us a little bit, but we still have some work to do on just getting the results looking sensible. And here in the top, you can especially see this these huge plumes of faint stuff coming off of the galaxy. So I guess it must be basically the debris from this first pass of the two galaxies. Okay. Okay, good. So, as I said, I think basically the big things to do immediately are improving this background subtraction, so removing those ripples. I think that can actually be done with pretty straightforward, just image processing sorts of things. I'd also like to do something sensible with weighting the images, so taking ones that actually sort of discovering which ones have longer exposure time or are more sensitive and weighting those more. Doing something about outliers that's more sensible. I have a feeling that outlier detection and duplicate detection should be something that can be done at the same time. So, especially for web search, you find 10 copies of popular images that have been maybe slightly modified or whatever. And they're not really providing new information, so it'd be nice to remove those. And I think there should be some way of sort of characterizing how surprising a new image is. Like if it's trying to make huge changes, then that might mean that somebody's made an annotation on the image or Actually, in one of the images we found in the data set, the person had either edited the image or made some error in composing it and actually moved the galaxy away from where it was supposed to be. So in their image, that was just blank sky. The rest of it was all fine, but it was moved somewhere else and labeled with an arrow to it and everything. Totally bizarre. But anyway, it seems like I'd like to figure out a way of characterizing that as like the surprisingness of an image. Like, if it wants to make huge changes, then it's probably not really right. And if it doesn't really want to make any changes, then it's probably something we've seen before. So it seems like you want to accept images that kind of are making little changes that are sensible. And then I think an avenue I'd like to look at is crowdsourcing rather than web search. So we'll actually try to recruit people to collect images for us with the hope of running this exercise on lots of galaxies and building up deep images and trying to detect and get a large census of these interacting galaxy streams and other science projects that happen to come up. Thank you.
Thank you for lots of lovely pictures and a lovely talk. Have we got any questions?
Hi. Cheers for the talk. So when you combine the images, you get a better signal to noise.
Right.
But one of the things with the telescopes, they have different intrinsic resolutions in terms of the angular size of the stars, right?
Yeah.
So then in your composite images, does this kind of like result in a kind of mixture distribution? And do you get actually a compromise on the angular resolution that you can resolve on the stars, but you just get more stars coming through? I mean, what's the balance?
Yes, exactly. Perfect.
Yeah.
Yeah, exactly. So, imagine. Yeah, exactly. Imagine that, one of the images is out of focus. That will contribute something about the stars, but it'll be a kind of a big blobby idea of where the star is. So yeah, it will degrade the angular resolution, compared to the best one in the bunch. That's actually another reason to go after these kind of faint diffuse features rather than, measuring stars as such. Because it really cares about, relative rankings of fairly large patches of the sky. So, but yeah, that's kind of another issue that really needs to be worked.
Have you tried to estimate how many images you would need to get to the Hubble resolution?
Good.
Which is what you compare to, is your gold standard?
That gold standard was actually not Hubble at all. It was a guy, a Spanish fellow,
Oh, right.
David Martinez Delgado. But anyway, he uses small telescopes and takes just very, very long exposures. He'll spend months. And basically, he has to use small telescopes because you can't get a month of a large telescope time to sit on one galaxy. Like, we don't have enough. That proposal would never get accepted.
Right. Have you tried to estimate how many images you would need?
No, not exactly. But it would be, basically, if you had a month of exposure time in total.
And what does that mean in terms of number of images?
An hour, 30,000 per night, 1 million seconds of exposure time. Say 10,000 at a minute each would be a good start.
Okay. Well, let's thank the speaker again.